Buried in the badlands of Patagonia lies a fossil that should not exist. A predator frozen in stone. 8 meters of muscle and bone, built for explosive speed with jaws designed to shear through flesh, and arms barely 60 centimeters long. For decades, paleontologists called them evolutionary failures. Useless limbs destined for extinction. Textbooks labeled them atrophied appendages. Scientists moved on to study the impressive parts, the horns, the powerful legs, the reinforced skull. But in 2017, a team placed those tiny bones under a CT scanner. What they found inside changed everything. Complex muscle attachments, fully articulated joints, a shoulder blade proportionally larger than in creatures with functional arms. This was not evolution giving up. This was evolution doubling down. When natural selection fights to preserve a feature for 8 million years, there is always a reason. A reason hidden in the microscopic details of fossilized bone. A reason we have been looking right past. Chubut Province, Argentina. Fossil hunter Jose Bonaparte is excavating badlands that have not seen rain in weeks. The sediment crumbles like ash. Buried 3 meters deep, he uncovers something extraordinary. A skeleton. Nearly complete. 8 meters from snout to tail tip. Skull crowned with 2 forward-projecting horns rising like weapons. Carnotaurus sastrae, the meat-eating bull. At first glance, another large theropod. Powerful digitigrade legs built for pursuit. Reinforced neck vertebrae. Blade-like teeth lining the jaws. But as Bonaparte's team excavates further, they stop. The arms. 60 centimeters total length on a 2-ton predator. To put that in perspective, imagine your arms could not reach your own stomach, could not touch each other held straight forward, could not grab, manipulate, or assist in any obvious way. What were they for? The discovery sparked immediate debate. Evolutionary holdovers, some said. Slowly disappearing as jaw power took over. Others suggested mating assistance, though the mechanics seemed implausible given the size. Most paleontologists cataloged them as an evolutionary quirk and moved on. The arms became a footnote, but footnotes sometimes contain the most important information. Natural selection is ruthless. Every feature must justify its existence or disappear. Consider a deer's antlers. They grow and shed annually. Tremendous metabolic cost. Calcium, phosphorus, energy that could build fat reserves or muscle. Yet deer maintain them because reproductive advantage outweighs the cost. Evolution tolerates nothing wasteful. So when Carnotaurus maintained fully functional arms across millions of years, across thousands of generations, the question isn't why they. The question is why they existed at all. National University of Cordoba. A team obtains permission to perform a computed tomography scan of specimen MACNCH 894, the holotype, the only complete Carnotaurus skeleton ever discovered. They create 3-dimensional digital reconstructions, revealing internal structures invisible to traditional examination. What they find contradicts every assumption about vestigial limbs. The humerus displays pronounced muscle attachment sites, deep grooves where powerful tendons anchored, and rugosities indicating substantial soft tissue. The radius and ulna show no fusion, no simplification, and the scapula, the shoulder blade, is not reduced. The scapula is proportionally large. In proportion to body size, it is larger than many theropods with fully functional grasping arms. This is where the anatomy becomes impossible to ignore. Vestigial structures follow predictable patterns. They simplify, lose complexity, and atrophy. The human appendix once belonged to a larger cecum that processed plant matter. Over millions of years, it shrank and lost compartmentalization, becoming functionally inert. Cavefish that live in lightless environments have eyes that regressed into non-functional remnants over generations. Ostriches show wing bones that became hollow shells, simplified and reduced to vestiges. This is vestigial anatomy. Simplified, reduced, atrophied. Carnotaurus arms showed none of these signs. The elbow retained a full range of motion, including 90-degree flexion. The wrist maintained rotational mobility. The hand could pivot. The fingers, all 4 of them, had individual phalanges with distinct muscle attachments. 4 fingers. Not 3 like most theropods. Not 2 like T-Rex. 4. Each required blood flow, nerve innervation, and cellular repair operating every moment of the animal's life. This is not a structure shutting down. This is active maintenance. And maintenance costs energy. A modern crocodile at rest must maintain its jaw muscles, blood flow, nerve innervation, and cellular repair. Unused jaw muscles alone consume 12% of resting metabolic rate. Now imagine Carnotaurus, an active predator maintaining arms it supposedly never used. For 8 million years, across hundreds of thousands of generations. Natural selection does not allow that kind of waste, unless those arms were not wasted. Compared to Tyrannosaurus rex, the famous example of reduced forelimbs. T-Rex arms were small and often mocked, but examine them closely and you see genuine degeneration. Fingers reduced from 3 to 2, joints showing fusion, muscle attachment sites shallow and indistinct. This is evolutionary reduction. T-Rex was losing its arms. Given another 10 million years, they might have vanished entirely, like snake legs. Carnotaurus showed the opposite pattern. Every joint mobile, every muscle attachment defined, every finger independently articulated. This was not an arm dying. This was an arm specialized, used for something important enough that evolution fought to keep it functional even while miniaturizing. But specialized for what? First hypothesis, hunting assistance. Perhaps the arms gripped prey. Biomechanical analysis immediately ruled this out. The arms could not reach past the creature's own chest. They could not extend forward to contact anything the jaws engaged. They could not rotate inward to grapple or restrain. The range of motion was entirely wrong for predation. A second hypothesis was feeding assistance, perhaps manipulating carcasses or tearing open body cavities. Again, anatomy disagreed. The fingers lacked recurved claws typical of meat handlers. The wrists could not hyperextend like scavenging theropods. The arms were too weak and too short to generate force against anything the jaws could not handle. Every obvious explanation failed. Paleontologist W. Scott Persons published a detailed reconstruction, digitally rebuilding the soft tissues that once surrounded the arm bones. Using attachment scars, bone geometry, and modern reptile musculature, his team mapped where muscles were positioned and what directions they generated force. The results were unexpected. Primary shoulder muscles, deltoideus and supracoracoideus, were not arranged for pulling or grasping. They were positioned for pushing, outward, away from the body at shoulder height. This is bizarre for a predator. No modern carnivore uses forelimbs this way during hunting or feeding. Lions do not push sideways at shoulder height. Crocodiles do not extend legs laterally. Bears do not generate outward force at shoulder height. Joints. This motion serves no purpose in predation, no purpose in scavenging, no purpose in combat, unless you are looking at the wrong context entirely. Across the animal kingdom, when structures serve reproductive purposes, evolution maintains them regardless of apparent impracticality. Male fiddler crabs have one enormously oversized claw, sometimes half their body weight. Useless for feeding, a liability in predator evasion, energetically expensive. But during mating season, males wave these claws in elaborate displays. The reproductive advantage outweighs every disadvantage. Peacocks show tail feathers so extravagant they hinder flight and attract predators. Yet mating success ensures those absurd genes persist. Elephant seals, during breeding, use forelimbs not to swim or hunt, but to stabilize while mounting females. Awkward mechanics, inefficient motion, but reproduction demands it. Evolution obliges. Now examine Carnotaurus through this lens. Imagine a male attempting to mate with a 2-ton female. Both standing on powerful hind legs, tails counterbalancing, male torso pressed against the female's back. Physics demands stabilization. Legs provide primary support, yes, but the angle is precarious. Any lateral shift breaks contact. This is where those tiny arms become essential. Pressed against the female's flanks, shoulder muscles generating outward pressure. Not pulling, not grasping, but pushing. Creating multiple contact points, distributing weight, maintaining position. It explains the preserved muscle complexity, explains lateral force vectors, explains why evolution maintained full joint mobility. The arms were not for hunting. They were for ensuring the next generation. This hypothesis gained support from an unexpected source: sexual dimorphism studies. In many theropods, males and females show distinct skeletal differences. Males possess more robust skull ornaments. Females have wider hip canals for egg-laying. But in Carnotaurus, all 7 specimens discovered show remarkably similar arm proportions. If arms served a sexually specific function, we would expect variation. Larger arms in males, more robust attachments. Instead, consistency. Both sexes possessed similar arm anatomy. Function determined by behavior, not structure. Males use them for mating stabilization. Females, perhaps, during egg-laying or nest construction. Lateral bracing against burrow walls provided essential leverage. Anatomy identical. Application different. Yet mysteries persist. If arms served reproductive functions, why did not other abelosaurids develop similar adaptations? Abelosaurus, the family's namesake, shows reduced forelimbs but not this extreme. Majungasaurus possessed proportionally longer, more robust arms. What pressure drove Carnotaurus specifically toward this solution? We can only speculate. Perhaps the prey base in late Cretaceous Patagonia favored extreme jaw specialization. Perhaps mating behaviors lost to time required this adaptation. Perhaps a genetic bottleneck locked this body plan, persisting because it was just functional enough. Another puzzle, the developmental timeline. When did arms become so reduced? Did juveniles hatch with proportionally longer arms that shrank with maturity, or were they always miniature? We have no juvenile specimens. Every known Carnotaurus represents subadult or adult animals. Without a growth series, we cannot track arm development from hatching to maturity. Did young Carnotaurus use their arms differently? Did juvenile hunting strategies make arm function more relevant? These questions remain unanswered, buried with countless individuals whose fossils we will never find. The four-finger configuration presents another enigma. Most large predatory dinosaurs reduced their hands to 3 functional digits and sometimes to 2. T-Rex retained only 2 functional digits in most individuals. Allosaurus kept 3, yet Carnotaurus retained all 4 fingers, each with distinct phalanges and clear muscle attachments. Why? 4 fingers do not provide obvious advantages over 3 for applying lateral pressure. Perhaps reduction happened in reverse. Digit thickness may have been sacrificed to preserve digit number. Perhaps 4-fingered hands served other functions earlier in abelosaurid evolution, and they were never lost because the energetic cost of maintaining 4 thin fingers was lower than the genetic cost of developmental reorganization. Evolution is not an engineer with blueprints. It is a tinkerer modifying what exists. Sometimes the results seem needlessly complex because simplification costs more than maintaining complexity. Consider the wrist mobility. Most vestigial structures lose articulation first because joints require synovial fluid, cartilage, and nerve innervation. Constant cellular upkeep. Expensive. Yet Carnotaurus wrists remained fully mobile. Pronation and supination, rotating motions that twist palm up or palm down. Why preserve this if arms barely reached past the body? One possibility is that rotational stability mattered. When a Carnotaurus generated lateral pressure against an unstable surface, such as a female flank shifting with breathing, wrist rotation allowed continuous contact despite surface irregularities. Like a human hand against a wall, minor wrist adjustments maintain contact. Not dramatic, not powerful, but functional enough to justify maintenance costs. The horns add complexity. Carnotaurus is named for its cranial ornaments, forward-projecting structures rising above the eyes. For years, researchers assumed a combat function, imagining males crashing horns like bighorn sheep. However, biomechanical analysis shows horn cores are too thin, and the skull is too lightly built for high-impact collisions. More likely, the horns served as visual displays, signals of health and genetic fitness. In this context, Carnotaurus becomes an animal shaped by sexual selection on multiple fronts: horns for visual display at distance, arms for physical stability during mating. Both features are costly, and both persisted because reproductive success demanded them. This paints a picture of intense mate choice and male competition driving evolution of seemingly impractical features that nonetheless increased breeding opportunities. What did Carnotaurus hunt? Fossil assemblages from the Anacleto Formation include hadrosaurs, small ornithischians, and various small to medium theropods. Carnotaurus teeth were not serrated bone crushers like T-Rex. They were flatter and blade-like, designed for slicing soft tissue rather than crushing armor. This suggests prey without heavy protection, perhaps juvenile hadrosaurs or smaller dinosaurs that were vulnerable. Perhaps Carnotaurus was an opportunistic predator, taking whatever prey powerful legs and fast, slashing attacks could overwhelm. Arms seem irrelevant in these hunts. The jaws did all the work. That reinforces their probable role in reproduction, not predation. Climate and environment may have played roles we do not understand. Late Cretaceous Patagonia was warmer than today, and seasonal rainfall created wet and dry periods. Did Carnotaurus breeding synchronize with those seasons? Did mating occur when food was abundant or when it was scarce? Seasonal breeding intensifies male competition. All reproductive opportunities were compressed into narrow windows. If Carnotaurus males competed fiercely, even small advantages in mating stability, advantages those unusual arms conferred, could determine success or failure. A male maintaining position 5 seconds longer might fertilize one additional clutch per season. Over a lifetime, that difference compounds. Over thousands of generations, that rewrites the gene pool. We must also consider what we do not know. Soft tissues are missing. Carnotaurus preserves skin impressions, showing large non-overlapping scales and scattered tubercles, but no musculature, no tendons, and no subcutaneous fat. Muscle reconstructions remain educated guesses based on bone geometry and modern analogs. Perhaps the arms possessed muscles we cannot detect. Perhaps connective tissues distributed forces in ways we have not modeled. Perhaps biomechanics in life differed substantially from digital simulations. We work with fragments and extrapolate to wholes, but the gulf between is vast. Even the holotype presents limitations. It is an adult, determined from bone fusion and overall size. We do not know if it was male or female. We do not know if it died young or old relative to the species' lifespan. We do not know if it was healthy or diseased, typical or aberrant. Every conclusion about Carnotaurus as a species rests on this skeleton and 6 fragmentary specimens. Imagine if all human knowledge came from 7 skeletons. We would miss countless variations, behaviors, and details defining what it means to be human. The same applies here. What we call Carnotaurus might represent only a narrow slice of what that species was. Technology offers new possibilities. Advanced CT scanning reveals microstructural bone details, blood vessel channels, and cell organization. These features might indicate growth rates, metabolic rates, and stress patterns from repeated motions. If Carnotaurus arms show stress consistent with repetitive lateral pressure, it strengthens the mating hypothesis. If they show no stress, suggesting minimal use, we are back at the beginning. Isotope analysis might reveal diet, seasonal patterns, and migration behaviors. Each technique opens windows into ancient lives, but windows are not doors. We see through. We do not pass through. The strangest aspect might be how much this mirrors other evolutionary puzzles. Why do peacock spiders perform elaborate dances despite the energy cost? Why do narwhals grow spiral tusks that serve no obvious survival purpose? Why do deep-sea fish possess bioluminescent lures that attract both prey and predators? Evolution optimizes for reproduction, not efficiency. An animal does not need perfect design. It only needs to be slightly better at passing genes than the competition. Sometimes slightly better means features that seem absurd through survival's lens. But reproduction is not survival, it is legacy. And legacy tolerates absurdity if the result is offspring. Carnotaurus forces us to confront the limits of fossil interpretation. We measure bones with micrometer precision. We model joint ranges with computers. We reconstruct muscles based on rigorous comparative anatomy. But behavior does not fossilize. Motivations do not preserve. The lived experience of being Carnotaurus, hunting through Cretaceous forests, navigating social hierarchies, seeking mates, and raising young, remains forever inaccessible. We build narratives from fragments. We construct stories from shadows. We must acknowledge, if honest, that our stories might be wrong. Yet even in uncertainty, there is value. The process of questioning, examining evidence from every angle, and discarding comfortable assumptions when anatomy suggests otherwise is how science advances. Carnotaurus does not offer easy answers. It offers better questions. Why would evolution maintain complex anatomy in reduced structures? Under what circumstances do reproductive pressures outweigh survival pressures? How do we distinguish vestigial features from specialized ones? These questions extend beyond one peculiar theropod. They touch fundamental principles of how evolution operates, how anatomical form reflects behavioral function, how we reconstruct the biology of creatures separated from us by an abyss of time. In the windswept badlands of Patagonia, stone holds fragments of answers. Each fossil is a word in a language we are still learning. Carnotaurus sastre, the meat-eating bull with arms too small to hunt and too complex to be useless, stands as a reminder that evolution's solutions do not always make intuitive sense. The strangest features often serve the most essential purposes. What appears broken might be perfectly adapted for a role we never imagined. Those tiny arms, dismissed as evolutionary footnotes, might have been the very reason Carnotaurus succeeded. Not in killing, not in survival, but in solving the only problem evolution cares about: passing genes forward. Ensuring the next generation, achieving genetic continuity across millions of years. Success isn't measured in size or strength or obvious power. It's measured in offspring, in lineage persistence through deep time. Carnotaurus, with its impossible anatomy and mysterious adaptations, thrived not despite strangeness, but because of it. And somewhere in the Anacleto Formation, in rocks we haven't excavated, in fossils we haven't discovered, lie more pieces of this puzzle. More fragments of a story written in calcium and time. More evidence of a world so different we can barely conceive it. Yet conceive it we must, because understanding how life adapted 75 million years ago helps us understand how life adapts still. The questions change. The principles remain. Evolution doesn't optimize for perfection. It optimizes for persistence. And sometimes persistence requires features that seem, to our eyes, utterly impossible. The arms of Carnotaurus stand as proof. Small, strange, and absolutely essential in ways we are only beginning to understand.